It's a little different.
Hello, this is the third section of chapter 11. So, we're going to talk about critical points. Critical point is where you cannot tell the difference between a liquid and a gas. So, the idea is what makes something a liquid is the fact that there is an attraction between the molecules, and that attraction yields a liquid phase. Uh, but what you can do is you can apply so much temperature to something that, and well, that's why things boil, is that the temperature, the average kinetic energy is higher than the intermolecular forces. But then you can have something at a really high temperature, but then put enough pressure on it that it has the same volume as a liquid. So this phase is beyond what we would consider the liquid or the gas phase. This we call the critical point. So where the kind of the difference between a liquid and a vapor no longer makes any sense. And we'll talk a little bit more about this later. So what? Why do you care? This is how we decaffeinate coffee. Certain properties of materials change past the critical point. So carbon dioxide, for instance, can dissolve caffeine past the critical point. You can use the Swiss water method, use supercritical water instead. So there's different ways you can decaffeinate coffee, but it's not just decaffeinating coffee. It's types of extraction for materials. So separation of materials is used for that. Okay, so next thing to talk about is a heating curve. So if you look at this chart here, on the y-axis is the temperature in degrees Celsius, and the y-axis is temperature, the x-axis is energy added. So imagine you take a block of ice from your freezer at negative 25 degrees Celsius and you apply heat to it. What happens is that the ice will heat from negative 25, assuming you're at atmospheric pressure. It'll go to 0 degrees. At 0 degrees, it'll start to melt. But the energy change, so the amount of heat is equal to mass times the specific heat capacity times the change in temperature. If you want, you can have mass times the specific heat capacity be the actual heat capacity. Then the melting point, at point number 2 on the chart, this is the heat is just the heat of fusion of, well, in this case, ice, whatever material you're looking at, times the number of moles. Then number 3, this is liquid water. The heat is going to be mass times specific heat capacity times change in temperature. And then at point number 4, the liquid is boiling. As it boils, the total energy transfer is going to be the heat of vaporization, or the latent heat, times the number of moles. And then we get to steam at point number 5. And then the heating up the steam, heat is mass times specific heat capacity times change in temperature. And the specific heat capacity for the solid, liquid, and vapor phase, they're different. So they're not all the same for the material. For water, it's about 2. It's close to the same for ice and steam. And there's about 2 joules per gram degree Celsius. For liquid water, it's 4.18 grams or joules per gram degree Celsius. Now, let's talk a little bit about the vapor phase number 5. Right when the steam boils, that's known as saturated steam, or also known as wet steam. So wet steam, well, it's called wet steam because if you walk into it, you get wet. And then if you superheat the steam past, so you can see the point number 5, it goes up higher. That is also known as superheated steam, or also known as dry steam. So why is it called dry steam? Because if you get hit by it, it doesn't condense. It just loses energy. And superheated steam, this is used in steam turbines and in power plants. At least non-nuclear power plants. Nuclear power plants actually use saturated steam. Typically, it depends on the plant, but they can use saturated steam. Why? Well, they don't like to raise the temperature too hot in nuclear power plants. But every other plant that uses a boiler, like here on Maui, the boiler. I'm doing this for sure, but they would be stupid if they didn't superheat the steam. So almost every place, and Navy vessels also superheat the steam, and that's nice because when you have a turbine, the steam comes in, steam comes out, and then the steam just loses energy. So and it runs the energy loss equals the energy transfer to the turbine. In saturated steam, the steam will condense on the turbine, which will make it less efficient, and also tends to damage and corrode the turbine at a more quick rate. And dry steam can be dangerous because if there is an explosion or something like a steam line ruptures, people tend to lose pieces of themselves. So like you can get like a cone-shaped burn put through your arm, something like that, with a firefighter or a Navy engine room mechanic, something like that. Dry steam can be very dangerous. So like if you go to a steam room in a workout facility, that's wet steam, that's saturated steam. So, but here's the heating curve. Another thing to point out is that you can see at the phase changes at point number 2 and point number 4 on the chart, the temperature doesn't change. So that is partially true. The real truth is, so this would be true for crystalline solid. How most solids, the heating curve would actually kind of look like this. It would be a slight increase like that, and that's because there's just different crystal structures, and it's because most solids are known as as amorphous, meaning there's different crystalline structures there, and the crystalline structures are going to melt at different temperatures. Not much, but it tends to be a slight incline in temperature. And then if you're going the other way around, if you're cooling, the curve could look like this. So where you get a little bump down here, right as, and the temperature is still the x-axis. I'm sorry, the temperature is the y-axis, and the x-axis is heat added or subtracted, or you could argue time if you throw it in the freezer. So that this little lip right here, this is known as a supercooled liquid, and you can get the liquid to be liquid phase and slightly below the melting point, and it forms a metastable or sort of stable state. It's kind of fun. I like to make slushies, or like if there's a hurricane, I put water in the freezer, and when it gets to the super cold state, you can take the water and you can whack it, and that'll provide the activation energy, and the whole thing will freeze like instantaneously. It's a lot of fun. A lot of fun to do that. At least I think it's fun. But okay, so why am I teaching this? Because when you have a heating curve and you're going to have some homework problems and test questions on this, you just add the different, for the total heat, you add up each step. Okay. Next thing I'm going to talk about is phase diagram. So here is the phase diagram for water. And water is a strange substance. So these are not to scale, but the y-axis is pressure, x-axis is temperature. And so if you notice a couple things, so the first block there, the darker blue, that's solid. The lighter blue is liquid, and the lightest blue is gas, the vapor phase. So, when the solid goes direct to a vapor, that process is known as sublimation. And when the gas goes to solid, that's known as deposition. Also, when I've marked up there, when a solid goes to liquid, that's known as melting. When the liquid goes to solid, that's known as freezing. When a liquid goes to vapor, that's known as boiling. And when vapor goes to liquid, that's known as condensation or condensing. So, and water is strange. What's strange about water, among other things, is that this curve goes this way. So that's not typical for most solids. Most solids, I've drawn here in the orange, this part here, that is how most compounds or elements go. And a couple things I've also noted, these horizontal lines, these are known as isobars. So iso, same barometric pressure, same pressure. And these vertical lines, these are known as isotherms, so same temperature. And you can also see the liquid phase does not exist for all temperatures and pressures, that there is a minimum point where it exists. And there's also this weird point here called the triple point, where all three phases are in equilibrium, or can be in the same point. So at the triple point, I've never seen it for water. It's pretty low pressure for water. I've seen it for carbon dioxide. It's about 5 atmospheres, and it's so. Solid carbon dioxide sinks in liquid carbon dioxide. That's another thing that's weird about water is that one of the more common solid forms floats in the liquid. But there's so imagine solid white dry ice and clear liquid CO2, and it's bubbling, so it's boiling. That's what the triple point of CO2 looks like. It's pretty cool to see. And then I've already mentioned the critical pressure and critical temperature, and the supercritical fluid. The properties change depending on the material. So there's a phase diagram. Here's an expanded phase diagram. So similar things, pressures on the y-axis, temperature on the x-axis, and you can see ice one. Ice one, I've only seen ice one in my entire life. I've never seen the other forms of ice. It's the most common type of ice, and it floats in the solid. There's other more dense form of ices, and one of these, I'm not sure which one it is, these ices, but it's also known as methane hydrates. And these other forms of ice, they can be heavier than liquid water, and we see ice on the bottom of the ocean. In some places, hundreds of meters thick, and in much of these places we have methane hydrates. We see them also around the Arctic, so in Alaska and Russia, and as these melt, they also release methane. And so Russia and Alaska, this is some of our primary sources for natural gas. If you can follow with the politics that go on with Russia, Russia supplies much of the natural gas to Europe, for instance, and there's always politics involved in that. They get their natural gas from their methane hydrates. And another thing about methane hydrates, so it's ice that will burn. So if you have a block of ice and you can light it on fire, and this is dangerous because one of the easiest ways to construct roads is to use explosives to clear things like dirt and go through hillsides. If you do that, or if you're building a building foundation, you usually use explosives to build out the basement and the foundation of a building. If there happens to be a patch of methane hydrates there can be a huge explosion. So that happens sometimes in construction in Russia. So with those methane hydrates. I already mentioned here, so isotherm, isobar. Here is iodine. So here is another material. So y-axis is still pressure, x-axis is still temperature. But you can see that, well, water, this line went this way, at least for the lower pressures, more common forms of ice, at least here on Earth, at least at atmospheric pressure. So as I said, there's different forms of ice in a really dense environment like the bottom of the ocean. Iodine has the more common way, the solid liquid phase going this way, where the solid phase is more dense than liquid phase. And then also here's carbon dioxide I showed you. So it's 5.1 atmospheres, but 5 atmospheres there, about 5 atmospheres for the triple point of CO2. So you actually can't see it. And carbon dioxide, it sublimes at this pressure. So if you have dry ice, it's a lot of fun to play like hockey with. And I mentioned water. Water is a very strange substance. Ice is slippery. There are very few solids that are slippery. And the reason why ice is slippery is because there's a thin film of liquid water on ice, and it varies with temperature. So I used to live in Wisconsin, and when it's cold, when it's really, really cold, like negative 30 degrees, ice is not slippery. You can walk on it. It's like walking on rocks. It's not slippery at all. But close to freezing, it's really slippery. And depending on the temperature, close to freezing, that's a pretty high level of water, liquid water on the surface. And as it gets colder, that liquid water layer drops. So water is also a very powerful greenhouse gas. It is the greenhouse gas in the Earth, corresponding about 90 to 98% of the natural greenhouse effect. I mean, it depends on if you include cloud coverage or not. If you include the clouds, then Water corresponds about 98% of the natural greenhouse effect of the Earth. And that's also slightly to say what causes global warming. So the idea is that carbon dioxide is not a very strong greenhouse gas, but water is a very powerful greenhouse gas. So the carbon dioxide evaporates more water, and that's the process known as climate forcing. So that's the idea that how the computer models make up for the difference in the weakness of carbon dioxide as a greenhouse gas for global warming. And to give you another example, so Mars has an atmosphere that's almost pure carbon dioxide. It's got, well, at least it has a lot more carbon dioxide than the Earth does, like a factor of 20. The difference between night and day in Mars is about 60 degrees Celsius. So nights get really cold. The moon can be on the order of 300 degrees Celsius. So it's the Earth has, depending on where you're at, it's maybe 5 or 10 degrees Celsius difference. I mean, on average, it's the Earth's change in temperature is very, very slight. We have a very, very good insulated atmosphere. We have a very strong greenhouse effect. Not as much as Venus. Venus, of course, has a much more pronounced greenhouse effect than the Earth does. But we have a nice one. And if it wasn't for it, the average temperature of the Earth would be about negative 15 degrees Celsius. The average temperature of the Earth is about 15 degrees Celsius. So we have about a 30 or so Celsius increase in temperature from our greenhouse effect, which is what allows us to have liquid water on the surface. So, and then when we get that, and that pretty much comes from water. And if you go somewhere where there's less water, like the desert, so if you've ever been in a desert, it gets really hot in the day and really cold at night. And that's what the Earth is like without the greenhouse effect. Water has a very high heat capacity. It's not the highest heat capacity, but it has a pretty high heat capacity. We live in Hawaii. At least you may be taking this class in a different state or country. But Hawaii, with a few exceptions, we never really get below freezing. I mean, yeah, maybe the top of Haleakala or Mauna Loa, Mauna Kea. But our cars, though, we have antifreeze in our car. Why do we have antifreeze in the car? Because ethylene glycol, which makes up 50% of antifreeze, has a higher heat capacity than water. So that rather than have a special car made for Hawaii that has a bigger radiator, we have a smaller radiator that uses antifreeze. So, but we don't really need it. We could just use plain old water in our cars if we wanted to, but we don't. But it has, but like I said, water doesn't have the highest heat capacity, but it has a pretty high heat capacity. It's a great solvent, which so it means it can dissolve things in it, and that means that it's very good, very efficient at transporting nutrients and toxins. So we are very good at transporting nutrients in our bodies, and so in living systems, and also things like waterways. So lots of nutrients goes through in the ocean and in lakes and rivers. But then again, if you put toxins in there, water will move them pretty easily as well. You can also have a certain type of pollution called eutrophication. That's where too many nutrients are added to something. And some of it is natural, so you can get algal blooms. The algal blooms in Alaska, they come from seasonal changes. So algae grows until it's limited by some nutrient, and around Alaska, southern part of Alaska, it's sulfur. And with seasonal changes, the ocean currents change, and sulfur rises up from the bottom of the ocean, and there's a huge algal bloom. And then krill eat the algae, and then other bait fish eat the krill, and then whales come and they eat the bait fish and the krill, and that's we have a whole system that goes on here. The humpback whales come from Hawaii. They go up to Alaska and they gorge themselves on the krill. They come back down to Hawaii and they give birth, and then they repeat the process every year. So also algae, if we were extraterrestrial aliens looking at the Earth, we wouldn't think that humans rule this planet. We would think that algae does. Algae is responsible for about 80% of the atmospheric oxygen. So a lot of people think it's grass and trees. And they do contribute to the oxygen, but it's really from algae. Algae is really what alters the atmosphere here. So But so that's natural eutrophication. There can be some unnatural eutrophication. So phosphorus, for instance, if you add phosphorus to the Mississippi River Valley, you'll get algal blooms. And we've also banned the use of phosphates and as soaps in the Mississippi River Valley because it caused algal blooms. And then in spring runoff, frequently in the Gulf of Mexico, we get algal blooms from the nitrogen from the crops. So those are examples of unnatural eutrophication that can cause harm to the environment. So still about water, it's common solid, so there's more than one solid of water, but its common solid is less dense than the liquid. So ice floats, which is really weird. So if you want to do a little experiment at home, take some olive oil and stick it in the fridge, and you'll notice that as the olive oil freezes, it'll fall to the bottom of the if you have a glass. I mean, of course, if you can see it through it. If it doesn't, if you have a dark bottle, you won't be able to see through it. But if you have a clear bottle, you can see the solid olive oil at the bottom of the liquid olive oil, and that's how most solids work. It's like that. So, okay, that's it for this chapter. We will have a short chapter next chapter.